Hello, this lecture is based on the textbook Combinatorics and Graph Theory, section 133 on spanning trees. Let's begin with a motivation for spanning trees. Let's say that we want to implement a rapid rail system to serve 8 cities in the western part of North Carolina. Some of the cities are already joined by roads or highways, and we want to lay the track right along these roads. And due to the terrain, some of the roads are steep and curvy, so laying track along these roads would be expensive. So the Department of Transportation hired a consultant to study the roads and to assign difficulty ratings to each one. The rating accounted for length, grade, and curviness of the roads, but basically the higher ratings would correspond to greater cost. The graph here, call it the city graph, shows the result of the consultant's investigation. The number on each edge represents the difficulty rating assigned to the existing road. We want to be able to make each city accessible, but not necessarily directly accessible from every other city. One obvious way to do this is to lay track along every one of the existing roads. But we want to minimize costs, so this solution is certainly not the best, since it would result in a large amount of unnecessary track. In fact, the best solution will not include a cycle of track anywhere, since a cycle would mean at least one segment of wasted track. So this situation motivates a definition. Given a graph G and a subgraph T, we say that T is a spanning tree of G if T is a tree that contains every vertex of G. So the Department of Transportation needs to find a spanning tree of the city graph, and we would like to find one whose overall rating is as small as possible. Here there are 3 attempted solutions. If we look at the total weight of the 3 spanning trees, this one has the least amount of overall rating. But is this one really the best overall? This is what this section is about. Given a graph G, a weight function is a function that maps the edges of G to the set of non-negative real numbers. The graph G together with a weight function is called a weighted graph. Every connected graph has at least one spanning tree. In fact, normally a graph has many different spanning trees. A spanning tree of a weighted graph G is called a minimum weight spanning tree if the sum of the weights of the edges of the spanning tree T is no more than the sum for any other spanning tree of the weighted graph G. So here is an algorithm. This is, by the way, an example of what's called a greedy algorithm. So we start with a connected weighted graph G. The first step is to find an edge of G of minimum weight and mark it. So of all the edges of G, the one with minimum weight is this edge, which has weight 10. The second step is to look at all of the unmarked edges that do not form a cycle with any of the marked edges. Among those, choose an edge of minimum weight and mark it. So the edges that I should choose one with weight 20, and here there are 2. I could have chosen this one, but I chose this other edge with weight 20. And the third step, if the set of marked edges forms a spanning tree of G, then stop. If not, then we go back to step 2. So now we have we have to go back to step 2 because currently we don't have enough marked edges to form a spanning tree. So I cannot choose this edge with weight 20 because then I would have a cycle. So I look at all of the other unmarked edges, and the smallest weight is 25, so I mark this edge. And looking at the other unmarked edges that I'm allowed to choose, the one with weight 30 is my next marked edge because here 30 is the smallest value. And for the next step, I see 35 is the smallest value, so I choose this edge. And in the next step, I see that 40 is the smallest value, so I choose to mark this edge. And finally, I see that if I want to have so I cannot I cannot mark 45 even though it's smaller than 50 because then I would have a cycle. So I choose 50, and now I have a spanning tree for G, and if I compute the total weight I get 210. So 210 is the smallest value in terms of the rating. So the theorem is that this algorithm produces a spanning tree of minimum total weight.